There's this wild paradox at the heart of engineering. On one hand, it demands incredibly precise, rigorous mathematics and physics. But on the other, it exists entirely to solve chaotic, poorly defined, and constantly shifting human problems. Welcome to today's Explainer, where we're going to unpack exactly how engineers manage to bridge that massive gap between an abstract human desire and a physical, working reality. To ground our explainer today, let's look at how the Accreditation Board for Engineering and Technology, or ABET, formally defines it. They describe machine design as the process of devising a system, component, or process to meet desired needs. Notice what's missing there? It doesn't just say doing math. At its absolute core, engineering is a deeply creative, iterative decision-making process. It's all about applying basic science to satisfy a very real human desire. Okay, let's really dive into this. Design isn't just crunching numbers in a vacuum. It's a massive, interconnected web. Sure, mechanical engineering intersects with materials science and solid modeling, but look at all these other branches. An engineer is constantly pulling from ethics, safety, sustainability, economics, and even aesthetics. You literally have to weigh the finances just as heavily as the tensile strength of the steel. So here's our roadmap for the explainer today. 1. The art of machine design. 2. The 7-step design process. 3. Taming the ambiguous problem. 4. Mechanics, materials, and math. And 5. The modern design engineer. Part 1. The art of machine design, balancing countless real-world variables. Picture trying to juggle up to 26 different, often competing characteristics on a single project. You want maximum functionality and total safety, right? But you also have to keep the cost down. You want the part to be incredibly strong, but it also needs to be lightweight with a low environmental impact. Recognizing all these factors and prioritizing them perfectly, that balancing act is where the true art of machine design lives. Section 2. The 7-step design process, creating order from chaos. This flowchart basically illustrates the engineer's hero's journey. To keep from getting overwhelmed, they loop systematically through this process. You start with conceptualization, move to synthesis to generate ideas, then analysis of the mechanics, material selection, the actual design calculation, evaluation, and finally representation, like technical drawings. And notice the feedback loops. It's totally iterative. If an evaluation fails, you loop right back to synthesis and try again. Moving on to part 3, taming the ambiguous problem, designing a boom with 0 instructions. This brings us to the daily reality of the job. Imagine a client asks you to build something, but they leave out half the necessary information. How do you actually create a mathematically perfect physical solution from a totally incomplete request? Let's look at a classic, poorly posed problem from our source material. You're asked to design a boom to hold a platform carrying up to 3,000 kilograms in a workshop. Okay, sounds simple. But wait, nobody tells you how big the boom should be? Nobody tells you if the platform uses a single-point or multi-point hanging method? They don't even tell you how to bolt the thing to the wall. Real-world problems are messy, ambiguous, and full of contradictions. Because the initial problem is so open-ended, the synthesis phase goes wild. Engineers get to brainstorm completely different physical structures. Just look at these two ideas. We've got a rigid truss system on one side and a cable suspended frame on the other. This just proves that in engineering, solutions are never unique. There are a dozen ways to hold 3,000 kilograms, which means out-of-the-box creativity isn't just nice to have, it's mandatory. After evaluating all those wild options for cost and simplicity, we eventually narrow it down to this design idea. It uses a simple circular tension rod connecting the top mount to the end of a square compression strut at the bottom. It forms a really strong, clean, triangular brace against the wall. It's simple to build, and it gets the job done. Section 4. Mechanics, materials, and math, proving it won't break. Now it's time to build the mathematical foundation. Using statics analysis, specifically looking at the equilibrium of forces at the outer tip, point B, we pinpoint the invisible forces at play. Because we're hanging about 30 kilonewtons of weight, our bottom arm faces a crushing 40 kilonewtons of compression, while that top circular rod is being stretched by 50 kilonewtons of tension. With those massive forces mapped out, we move to material selection. We pick mild steel, specifically AISI 118. It's ductile, which is perfect for this. Our key metric to watch here is yield strength. That's the exact point where the metal essentially gives up and permanently bends under stress. For this specific steel, that natural yield strength is 370 megapascals.
But here is the golden rule. We never, ever design right up to the breaking point. If it yields at 370, we're definitely not planning for 369. We apply a design factor. Here, we're using a design factor of 2. Think of it like an insurance policy. It's like building a bridge to hold twice the expected traffic just to be absolutely certain it survives any unexpected wear and tear.
This creates a rock-solid design philosophy. The actual maximum working stress, the forces the part will realistically experience, must never exceed our allowable stress. So we mathematically slash our safety threshold in half. We take that 370 megapascals yield strength, cut it by our design factor of 2, and we get a strict allowable tensile stress of 185 megapascals. Time to crunch the final numbers. We take that halved allowable stress of 185 megapascals and cross-reference it with the 50 kilonewtons of tension stretching our top rod. Running those numbers through the area formulas, we find our steel rod needs a diameter of at least 18.5 millimeters to safely operate. Just like that, we've converted a messy, ambiguous problem into a precise physical dimension. But we're not done. The math covers literally every inch of the structure. Engineers meticulously evaluate everything. They calculate the normal stresses. They calculate the shear stress trying to slice the nut right off the bolt. They check the double shear at the pin connections. They even calculate bearing stresses, that intense pressure where a round pin pushes against the flat inside of a hole. Every single nut, bolt, and point of contact has to be mathematically proven safe. Finally, Section 5, the modern design engineer, the ultimate multi-tool. Today's design engineer is basically a human Swiss Army knife. You can't just be good at math anymore. You've got to be an excellent communicator to decipher those ambiguous client requests. You need hands-on manufacturing experience so you don't design something that's literally impossible to build. You need CAD mastery, sharp creativity, an understanding of environmental laws, and the agility to adapt to new tech. Bringing us full circle back to where we started. Every single calculation, every wild brainstorm, every safety factor we've talked about serves one noble purpose. As the source material reminds us, the main objective of any engineering design project is the fulfillment of some human need or desire. So we've unpacked this amazing paradox of the engineering design process. We've seen how it takes messy, incomplete human needs and uses strict methodology, creative synthesis, and rigorous math to forge a totally reliable physical reality. Knowing the incredible balancing act behind the machines and structures all around us, I want to leave you with this to chew on. What human desire will you engineer into reality next? Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.